Okay, so I'll continue from where I left off yesterday. So I was discussing this transverse field Ising model, and basically my aim was to start here. My aim was to give you enough machinery so that you can calculate the following graphs, following kinds of graphs yourself. So I'll just illustrate it. This is schematic. So you're driving a state of a transverse field Ising model, okay, which is an integrable theory, and then what you're plotting is at the end of, let's say, two drives, what is the entanglement entropy of L adjacent spins, okay? And of course this L can vary. It can increase, decrease or something, so this L, right? So so this is a graph which shows this very important point, which is general for unitary dynamics starting from pure states, that even if you start with unentangled states, as you evolve the state under unitary dynamics, whether it's dynamics from some undriven Hamiltonian or dynamics due to a Fluke unitary, whatever it is, it keeps generating entanglement in the system, and basically this graph is showing that. And what happens due to that is the information about the initial state is actually transferred as a function of time to more and more complicated non-local operators. And this is really at the heart of thermalization, as you have already been exposed to. But as you also have heard from Subrato's lectures, that these kinds of things are very hard to calculate for a generic system. You can only do it for small sizes using numerical techniques like exact diagonalization. So as I was telling you yesterday, the aim here is to try to calculate these kinds of things for the transverse field Ising model on reasonably big sizes, okay? So here also you have to do these things numerically. The only difference is you can easily access 10 raised to the power 5 lattice sites or even more, okay? Good. So let me just continue from where I stopped yesterday. So what we did yesterday was, so let me just write some of the basic things again. Yeah. So the model which we are going to be concerned with is the transverse field Ising model, where I have assumed periodic boundary condition on spins. Okay, and I'm being specially careful here because I just want to give you the bare bones to actually just set up this numerical calculation. So I'm just being careful about factors and what Fourier modes to sum, etc., etc. Okay, good. Then what we did was this Jordan-Wigner transformation. So the way this transformation happens is, so for these sites you just number in some ordered fashion, okay, and they live on a ring. So this is I plus 1, I plus 2, and so on. This is I minus 1, I minus 2, minus 3, okay. So there's this Jordan-Wigner string here. So the transformation is from spins to spinless fermions. That's the first step. Maybe I write it here. Oh, so CJ tag. This is J. Okay, yeah, that's correct. So this string operator, this object is a non-local operator, and this could be +1 or -1. Okay. Okay, so then you insert these things here, and you can verify that it goes to a free fermion Hamiltonian, and that free fermion Hamiltonian has two kinds of terms. One looks like this, the other looks like nearest neighbor hoppings, and the other looks like some pair creation and annihilation terms on nearest neighbors. Then we made the further restriction, okay, which is going to be important for me. We made the further restriction that we will always be in the sector with an even number of fermions. Okay. So this is partly motivated from the fact that if you take a ring with even number of sides, so capital L is even, and you look at the ground state, then you can show by doing this Jordan-Wigner transformation carefully, you can show that the parity of the fermions in that ground state is an even number, okay? And that's a conserved quantity, so the dynamics won't change it. So let me just, for simplicity, restrict to this thing, okay? If you restrict to this thing, this implies, in the language of fermions, that you have to adopt this boundary condition. So the fermions get an anti-periodic boundary condition because of this restriction, okay? Then you go to Fourier space of the fermions. That's the most natural thing to do because you have terms like this in your Hamiltonian. So you go to Fourier space, and I also carefully define the Fourier transform in a particular fashion with this phase factor, because I just want the Hamiltonian not to contain any i's or something. Of course, you could have chosen not to include this phase factor. You would still get correct answers with k being 2 pi m by L. And these m's are restricted to half integers like this. And for each k, there is a unique minus k. So there's no k equal to 0 here. For each k, there is a unique minus k. Okay? Good. Then, using this fact that for each k, there is a unique minus k, you can actually club terms together and write the Hamiltonian like this. So I just sum over k greater than 0 modes. So it's good to club terms and sum things like this, and you can write that sum. And then you will see that this can be written in a 2 cross 2 structure. So what is that 2 cross 2 structure? So in that 2 cross 2 structure, the upspin is this mode, and the downspin is just the vacuum of fermions. Okay? And then, if you just write this in terms of Pauli matrices, you get the following pseudospin representation. Okay? And of course, you can just do the dynamics of each pseudospin separately, right, with that Hamiltonian. And this is time dependent in general. And then the full wave function is, of course, ukt up plus vkt down. Okay, so you just need to find, so the aim is to find these guys, right? And then the full wave function is nothing but a tensor product of all these guys. But see, I'm just doing k greater than 0, right? So in this representation, so it's very interesting. It's just good to maybe draw a diagram here. In this representation, what you did was move from capital L physical spins. So let me just draw the physical spins like this. So there are capital L of them. So to indicate that these are physical spins, I put this label R, so they are in real space and they are denoted by this sigma variable. Then you went to these spinless fermions. These spinless fermions are also in real space and there are L of them, and so they live in real space. And yeah, so this diagram just suggests that, and they hop around and they pair produce and pair annihilate. Then I made a restriction to NF being even, because this theory has two sectors. One sector has an even parity of fermions and the other sector has an odd parity of fermions. I restrict to the sector with even parity of fermions. When I do that, then go to K space and do this pseudospin representation, there comes another natural representation where there are now L by 2 spins. All of you understand why? Because you see, I'm only concerned with the K greater than 0 modes. So there are only L by 2 spins, L by 2 pseudo spins. So let me write this tau. And these spins live in K space, in a different space, right? And each spin has its own magnetic field and does some dynamics. Right, like this. And you just take the outer product of all these spins and that's your many-body wave function. So you see, here there are 2 raised to the power L degrees of freedom. Here there are 2 raised to the power L by 2 degrees of freedom. But the reason that happened is I have restricted my Hilbert space here. If you took also the NF odd Hilbert space, you would get the additional states here. Okay, but I'm going to just talk about this. Okay, good. So far so good. Is everybody happy? Okay. Now the task is to calculate the entanglement entropy of L adjacent spins in this language. This seems a bit non-obvious at this stage because we have made some non-local transformations. So it's not completely obvious. See, what do I want to do? I want to get L consecutive sites here. So maybe I have chosen this site, this site, this site, and this site here. Okay? And I want to integrate out the rest of the degrees of freedom and I want to find the entanglement entropy of this subsystem. That's my aim, right? But I want to do this calculation for these guys. But the simple representation is here, right? So it's not completely obvious how you will do it because this is R space, this is K space, and anyway there's some further transformations, right? So it's not completely obvious. So let me just state that for you, how you'll do that. It's kind of interesting. So basically the point is so before we do calculations, I need to somehow tell you how to get the entanglement entropy in terms of correlation functions of the spinless fermions, right? But all of you can understand there are only 2 kinds of correlation functions in this problem. One kind of correlation function is this, and the other kind of correlation function is that, right? There's no other correlation function here because it's non-interacting fermions. So all higher point correlations can be reduced to these correlations by Wick's theorem, okay? So my aim is to somehow reduce this calculation to a function of these guys. So all of you are clear on what we want to do, right? Good. So that's the aim. And these guys, it's easy to calculate. It's easy to calculate it in terms of these UKs and VKs. Okay. So for finding the UKs and VKs, you need to go on a computer because unfortunately, if I give you an arbitrary time varying field, you cannot even solve the problem of the motion of a single spin half completely analytically. So, yeah. So, but that's okay. I mean, still you know how to attack that problem. Right? So that's much simpler than a full many-body problem. Good. So I have been harping upon the fact that these are L adjacent spins. So why am I doing that? They cannot be non-adjacent spins. So why am I doing that? So let's see. So the point is, so let me draw a schematic here. Let me show a subsystem with 3 spins. So why adjacent spins? So you see, you would like the calculation to reduce to the following. If you have a subsystem here, once you calculate correlation functions, you would ideally like to compute fermionic correlation functions only involving site I plus 1 and site I plus 2, right? You would not want to calculate a fermionic correlation function of maybe this site with some other very distant site here. Though in principle, you could have needed it because there's a Jordan-Wigner string. In principle, you could have needed it, right? But you don't want to do it. I mean, otherwise there's no advantage to this thing. If you have to go light years away to something else, yeah. So why does this thing save us? So you see, suppose I am looking at this spin. So there are only 2-point correlations which are important, and let's say I'm looking at that spin, right? So the Jordan-Wigner string of this spin is like this, the ith spin, right, this guy. The Jordan-Wigner string of this spin is like that, right? But now if you're concerned with only 2-point correlation functions, look outside this subsystem. The Jordan-Wigner string has pairwise cancelled off. The simple reason for that is, I mean, where was the string? So it was some term like 1 minus 2 Ci dagger Ci for any site, right? But there's another 1 minus 2 Ci dagger Ci for this Jordan-Wigner string. So this thing can be plus 1 or minus 1. This thing can be plus 1 or minus 1. But the point is, minus 1 square equals plus 1 square equals identity, right? So the Jordan-Wigner strings have cancelled in pairs, right? So you don't need to even consider the Jordan-Wigner strings when you compute 2-point correlation functions. That's the reason I took adjacent spins. Of course, the Jordan-Wigner string of this guy is hanging here, right? It's there, right? Or if you took a bigger subsystem, it's there, this guy, because this is not cancelled with this guy. But that's okay. That's a fermionic correlation function inside this subsystem. That's fine, okay? But the advantage of taking L consecutive sites here is that outside, I have just completely cancelled the Jordan-Wigner strings, pairwise. Because after all, it's a product of plus 1s and minus 1s. So whatever the sequence of plus 1s and minus 1s here is the same sequence of plus 1s and minus 1s here. So you can just club terms together, square them, and the result is identity, right? So that's it. So they have cancelled out. So that's a huge advantage. They have cancelled out outside the subsystem. They can still remain inside the subsystem, but that's okay. Those are some 2-point fermionic correlations that I'll calculate anyway. Okay, so that's the main thing. So, of course, so again, like Shubrata was,
just
yeah.
So the strings for I and I plus 1 cancel each other.
Any two things, yeah.
Any two.
Yeah.
Then L has to be like, what about I plus 2? So.
Oh, outside it'll still cancel. So if you do any pairwise thing, it'll still cancel.
No, I plus 1 they cancel. But
okay, let's look at I plus 2. See, this is the string. Sorry, the string actually goes from here. This is the string. They'll also cancel, right? Yeah. Now, let me go to what Shubrata was saying. So, in general, if you write the density matrix in terms of just correlation functions, you would need all correlation functions which are non-zero inside the subsystem, right? So, so I forgot where was the x. I think the x was in the transverse direction or which direction? Let me just remind myself. Yeah, okay. So, okay, yeah. So, for example, sorry. For example, you compute some correlation function like this at I. This is easy to compute. This is easy to compute. This is local in fermions, right? Suppose I compute some correlation function like that. This would vanish from the symmetry of the problem because it's a finite system. This would vanish, okay? But suppose I compute a correlation function like whatever, I plus 2. This I know again how to calculate in terms of fermions. Suppose I compute a correlation function like that. This is in general non-zero. This I also know how to compute in terms of fermions. So all these correlation functions, this is a higher point correlation function in terms of fermions, but I can reduce it, right? And so on, right? So all these correlation functions I know how to compute, right? So the key point is all of these correlation functions would reduce to some correlation functions in terms of the fermions, but because these are non-interacting fermions, all those correlation functions can be reduced to just functions of these. That's the key point, right? Good. So now the aim is how to get the entanglement entropy in terms of these guys. That's the aim. Okay, any question? Yeah, yeah.
You just told that since the system is finite, the sigma is in average is 0.
Yeah.
How
How
to see that?
to see that? You use the Z2 symmetry of the problem and you'll see that.
What does it have to do with finite or infinite size?
Oh, in infinite size, you can spontaneously break symmetries. Okay, so let me represent those two guys in terms of these matrices. So these are of course time dependent because your initial wave function is changing as a function of time. Right, so so note that when I'm writing this matrix, let me just write these two matrices, then I'll tell you what I mean. So please note that these i's and j's are completely inside the subsystem that you have taken of L adjacent sites. Okay, so this I can be this guy, this guy, this guy, this guy, or this guy. This J can also be any of these guys. So these are completely inside the subsystems. That's the advantage of taking these adjacent spins so that the Jordan-Wegener strings cancel out outside the subsystem. Okay, so all of you agree that these are two L cross L matrices. So something about these eigenvalues of these two L cross L matrices should tell me about the entanglement entropy, right? So what should I do? What kind of matrix should I generate so that its eigenvalues give me the entanglement entropy? So let's go over the steps. So actually I forgot, when did I start? 9:30, right? Okay, yeah. So, okay. So this reduced density matrix, whatever it is, if I go to the right basis of fermions so that somehow the problem becomes diagonal, then it can always be expressed like this. So this is the reduced density matrix. So it can always be expressed like this, where this HS is some, so this L is the same as that L. There are some fermionic modes like that. Okay. Because it's a quadratic problem, there must exist some transformation which would give you this. What that transformation is Maybe easy to find, maybe hard to find, but there must exist some transformation like that. So actually that transformation is called the Bogoliubov transformation. So in essence, in a nutshell, what you want to do is you have a problem where the original fermionic Hamiltonian has terms which are like C dagger as well as C dagger C. You want to go to a basis in which there are only terms like eta dagger, okay, something like that, okay. So just to actually convey the idea to you, and just to also set up notation, let me do a toy problem, just to illustrate this idea. I mean, this is done in various textbooks. I'll just introduce it in one way for two fermions so that the generalization to L fermions becomes obvious. So it'll be a quick way of introducing everything for you. So let's look at the following toy problem. So let's assume this epsilon and lambda real without too much loss of generality. So this is a simple problem, right? But in this simple problem, you see that there are terms like C dagger C and there are terms like C dagger, right? So the general way of diagonalizing this problem is the following. So you want to go from these fermions to some other fermions, okay? So this transformation is this. So I'll write a particular transformation where I'll go to some new fermions which are represented by D1 and D2 and D1 dagger and D2 dagger, okay? And when I write this transformation, there'll be a creation operator as well as an annihilation operator. Now I have a very good reason of writing the transformation like this, and I'll come to it. Okay, and if these guys are real, you can actually show that U and V are also real. Okay, if lambda is real, but let me not go to that. Okay, so why is this good? So I already told you that I'm assuming that these are also fermions, right? So they have a certain algebra, anti-commutation algebra. These anyway we know are fermions, so we know their algebra. So what happens is the following. If I write the transformation like that, then and assume that on the right hand side I have the usual fermion anti-commutation algebra, then two of the fermion anti-commutation algebra for these guys are automatically satisfied, and one thing is not automatically satisfied, and you have to put a condition for it, and that gives you a certain condition on U's and V's. That's it. So let me just show that. So this particular transformation that I have chosen automatically satisfies the following. You can check that. It satisfies these relations. C2. These are anti-commutation. Automatically satisfies this. But if you want to do the following, let's say C1 comma C1 dagger. If you want to do that, that should be identity, right? This thing should be identity. Then, if you just plug this thing in, you'll get something like this. Because anyway, I have assumed fermion algebra for these guys. Because I've assumed fermion algebra for these guys, this is equal to U square plus V square. But this I know should be 1, right? So I get a condition on U and V, right? That U square plus V square should be 1. So there is a natural way to parameterize U and V now, right? So what do you think I should do? Cos and sine, right? Exactly. So I just say U is cos V, V is sine. This is the natural parameterization. So all I need to know is, given a Hamiltonian, I need to find the appropriate theta, which diagonalizes this Hamiltonian into that Bogoliubov form. So I need to find a single angle which does the job for me. Now let me continue, and you'll see that there is a very nice geometric interpretation here. Okay? So basically, there's a very nice way of writing the transformation. The same equations. So I can write it like this. And you'll almost see what the geometric interpretation is, and then I'll continue and you'll fully see it. So if you write it in these variables, you can verify that the transformation is this. Can all of you recognize this matrix? This is nothing but a rotation matrix, right? So this is some 2 cross 2 unitary matrix, right? So already you see that there is some very nice interpretation here. Right? So this is a 2 cross 2 unitary matrix. So all I need to do is find an angle which gives me the diagonal form. But you see, I mean, from here it's obvious that the whole problem can be thought of again as a spin in a magnetic field, right? And all that you need to do is set your coordinate system along the magnetic field. There's only one thing that can happen for 2 cross 2 matrices, okay? So we'll see that. That's exactly what's going to happen. So the interpretation is there'll be some effective magnetic field. You just need to take your coordinate system along that magnetic field, okay? So let's see how to do that. So of course, for that, I need to look at the Hamiltonian, right? Because that is what gives me the effective magnetic field, okay? So the Hamiltonian is this, that guy. So let's write that Hamiltonian in a nice matrix form. Oh, maybe let me keep that here. Let me just go to this blackboard. Okay, let's continue from here. Okay, so let's write this Hamiltonian. I'm of course being a bit fast because I want to cover some ground, but the steps are not hard at all. You can fill up the missing algebra and verify everything. So you can show, so I'll write it as a 4 cross 4 matrix because that's what I need. So it'll be a block diagonal matrix, with these 2 cross 2 blocks being 0, and these 2 cross 2 blocks being non-zero. So again, it smells like a spin in a magnetic field, right? Because this is like a sigma z, this is like a sigma x. These epsilon and lambdas are exactly the ones there. This is minus of each other. Yeah, this is correct. C1 dagger. Okay, plus some constant. That constant is simply because to ensure that I get this form, I sometimes need to use anti-commutation relations like that. So of course, when I do this and I take something which is C1, C1 dagger to C1 dagger C1, I have a hanging identity. So these constants basically arise due to those kinds of operations, okay? Good. Now it has a block diagonal structure. So I can just focus on the upper block and the lower block separately. So let me just do that. Let me just focus first on the upper block. So this upper block and this upper block couples with just this matrix because there's a block diagonal structure here. And this lower block and this lower block couples only with this matrix because there's a block diagonal structure here. Okay? So let's just look at the upper block. So if you just focus on the upper block, then this thing, okay, I'm maybe ignoring some factors of half, but that's okay. Looks like that. Now, what was my transformation? My transformation was this, right? So let me actually make that transformation here, and then my aim is this 2 cross 2 is a matrix, is a non-diagonal matrix. My aim would be to insert this transformation and choose theta to make it a diagonal matrix, right? So then I just insert that transformation with an arbitrary theta here. So I just change from C's to D's by inserting this transformation there. And when I do that, I get the following. So the aim is to make this diagonal. So I need to choose theta to make this diagonal. But this is actually, I can do it even without computing anything. So how do you see what to do? So you see, as I said, think about this problem. This is just a spin in a magnetic field, right? This is the z component, epsilon is the z component, and this lambda is the x component of that magnetic field, right? So basically, there is a total magnetic field of this magnitude. Okay. So whatever that diagonal transformation is, the diagonal matrix will look like that. Sorry, this is minus. The diagonal matrix will look like that. All of you agree to that? This is the only thing that can happen. Nothing else can happen. Okay, so it'll look like that. Good. Now, what is the transformation which diagonalizes this? I know the z component of the magnetic field. I know the x component of the magnetic field. Therefore, I know the unit vector along which the magnetic field is. I just do a spin rotation so that my z-axis goes from the lap frame to that frame. And then this problem becomes diagonal, right? That's it. Okay? Good. So that fixes your theta. Okay? So that's done. So this is how you solve for a 2 cross 2 problem with Bogoliubov transformation. So at the end, all that Bogoliubov transformation does is to find this angle theta for you. Okay? So now let's generalize it to our full problem. So I hope the steps are clear to you, right? I'm almost sure that many of you must have seen this somewhere in your graduate school or something. I'm just interpreting it like that. Maybe you are already familiar with this interpretation. Maybe not, but that's okay. So let's go back to the original problem. Yeah. After I'm done with this problem, which is a bit algebra heavy, I'll tell you another problem where you can just sit back and relax, and I'll just draw pictures, and yeah, you'll see the physics there. But unfortunately, here I cannot draw pictures, right? So because I want to derive some relations. Okay. So back to the original problem. So in the original problem, basically, my degrees of freedom were, original degrees of freedom were Ci and Ci dagger, and I want to go to some correct, not correct, I want to go to some more convenient degrees of freedom, etas, let's say, and in those degrees of freedom, I want a diagonal form for this thing. So basically, well, this k is just an index, okay? It's not necessarily momentum. Basically, you can write the problem like this. Again, I need to mix the CIs with the CI daggers, right? That's the general philosophy of the Bogoliubov transformation. And of course, if you're given this, then writing the dagger is easy. You just star these guys. And this guy becomes a dagger. And that guy also becomes a dagger. Good. So basically, I can write a shorthand for this. This is a bit of a cumbersome notation. The shorthand for this is this is connected to this by this T matrix, where there are actually 2L entries here, 2 times small l, where L is again the size of your subsystem. Okay? So 2 times small l. So like C1 till CL, C1 dagger till CL dagger. Okay? So this T on general grounds, okay, see, this is a transformation from one set of coordinates to another set of coordinates. Therefore, T on general grounds must be a 2L cross 2L unitary matrix. Because I'm doing a basis transformation. Exactly like this is a 2 cross 2 unitary matrix. Exactly like that, this must be a 2L cross 2L unitary matrix. It cannot be anything else. It cannot be a non-unitary matrix. Otherwise, this cannot be represented as a transformation. Okay? And what is the form of this T? We can just guess it from here. Of course, we haven't found what these G's and H are. So what is the form of this T? Basically, again, I'm writing a shorthand, but you can all guess what this shorthand means. Star, G star. That's this T matrix. Good. Now let me introduce some further shorthand. I have a collective index for this, and I have a collective index for that. Okay, so the transformation now looks like psi is T phi. I'm just doing linear algebra, okay? But of course, I agree that maybe you have to go over these things once more to get everything clear in your head. But okay, so in terms of this, in this notation, there was, okay, there. I said that the reduced density matrix can always be expressed in that form, right? So the aim is to somehow write that HS, which is originally a non-diagonal matrix in terms of the original fermions, as a diagonal matrix in terms of the new fermions, right? So in terms of the original fermions, there's some matrix M which is non-diagonal, right? Now I want to diagonalize it. Now I just use the usual thing. So I want a T matrix which diagonalizes this thing, right? So let's just do that. So I know that this T matrix is a unitary matrix. So I can do this insertion because this is identity and this is also identity. So I can do this. Good. But why did I do this? Because from this, I know that, so okay, let me just call it not psi, because in my notes now I have called it eta. So sorry about this notation business. So yeah, sorry about that. So and this should be a diagonal matrix. Okay, in fact, if you look at the form of this diagonal matrix, so there's some D, which is some diagonal matrix, right? So basically, M is T dagger D, T, So if you look at the form of this diagonal matrix, it again looks like this. There's a collective epsilon 0, 0, minus epsilon t. So basically for any, so there's a collective epsilon, so epsilon 1 till epsilon n. For any epsilon 1 here, there would be a minus epsilon 1. For any epsilon 2 here, there would be a minus epsilon 2, and so on. Because it's just a direct generalization of this problem here. Okay, so the point is, here the things came in pairs. Here also the things would come exactly in pairs. Okay, so for every epsilon 1, there would be a minus epsilon 1. For every epsilon 2, there will be a minus epsilon 2, and so on. So basically, this 2L cross 2L matrix has to reduce to a bunch of 2 cross 2 problems, each with its own epsilon and minus epsilon. Why is that? Because when you go to the right basis, then these are all, after all non-interacting fermions, right? So somehow this interpretation has to be recovered, right? Where for these non-interacting fermions, if one level was epsilon, the other level was minus epsilon. The only difference here is that there are L copies of such thing. So if one level is epsilon 1, the other has to be epsilon 2. If one is, let's say, epsilon 2, the other has to be minus epsilon 2, and so on. So this structure has to be maintained here. There's no way out of it. Now we are almost there. Sorry for these long-winded steps. Now we are almost there. So now let me write a natural matrix here, which is the outer product of those guys. Why did I write this matrix? Because if you expand this out, this is nothing but a 2L cross 2L matrix which has all 2-point correlation functions possible in terms of CIs and CI daggers, right? Because this is nothing but a row with C1 and then whatever. This is similarly a column. So if you just form the matrix out of it, it has all possible 2-point correlations, right? Good. Now you carry this T transformation here. Remember, I haven't yet found out the T transformation for you. In fact, when I solve this problem, I'll solve it in such a way that I don't need to find out the T transformation, because actually finding it out is a bit difficult, because then you have to diagonalize some 2L cross 2L matrix, which might not be terribly small, but yeah. But we don't even need to literally diagonalize the matrix. We can get away with non-diagonalizing the thing. So again, I insert these unitaries here. Okay. So then this is the diagonal form. But in this diagonal form, the correlation functions are remarkably simple. If the problem reduces the diagonal form, the only non-zero correlation function in that diagonal form is the following. The only non-zero correlation function. That's it, from Fermi-Dirac distribution. Because this is a fermionic problem with an effective beta of 1, right? And like if you are at some appropriate, if you're looking at some appropriate mode eta k, then it has an epsilon k, right? So you know from Fermi distribution that this is what this thing should look like, Fermi-Dirac distribution. That's the only correlation function which can be non-zero here. All other correlation functions must be zero, right? So this comes from Fermi-Dirac. Okay, so then we have a beautiful form which is the following. So again, this epsilon is a collective index. Actually, it means epsilon 1, epsilon 2 till epsilon L. And of course, if there is an epsilon, there's a minus epsilon, right? So there would be a mode with a minus epsilon. But let's stare at this. This is some kind of a probability. So if there is a P, there's a 1 minus P. Now you already see the interpretation of entropy here, right? So you can just interpret this problem with fermionic modes. One mode is if it's populated with P, there's another thing which is populated with 1 minus P. So if one thing is populated with P1, there's another thing which is populated with 1 minus P1. If there's a P2, there's another thing which is populated with 1 minus P2, and so on. So now you all know how to calculate the entropy of such a problem, right? The entropy of such a problem is nothing but that's it, which is your entanglement entropy as well, right? So basically, if you go to the diagonal form of this matrix, which matrix? That matrix. If you go to the diagonal form of that matrix, then entries comes in pairs like P and 1 minus P. They don't come in epsilon and 1 minus epsilon. They don't come in epsilon and minus epsilon. If you go to that kind of a matrix, they come in pairs like P and 1 minus P. For every P1, there would be somewhere a 1 minus P1 if you go to the eigenvalues, okay? And of course, eigenvalues don't change under unitary transformation. That's the important point, right? So I don't even need to fully diagonalize this problem. All I need to now tell you is, what is this matrix C? That's all I need to tell you. Whatever this matrix C is, you just diagonalize that matrix. You will get a bunch of eigenvalues, 2L eigenvalues to be precise. And for each, and you can now have a unique, like a map from L of them to another L of them, where the map is if there is an eigenvalue whose value is P, and of course P can only lie between 0 and 1, there must be another eigenvalue whose value is 1 minus P, okay? And then you just take all those eigenvalues and you do this sum, and that's your entropy. So what is this? Now we are almost there. I'm sorry, the steps are a bit involved, but again, I hope I have given you enough steps so that you can fill out the rest of the details and understand it completely in your head. But once you get the hang of it, you will see that it's a very natural thing to do. So of course, if you see the first time, it looks a bit shocking. Okay, so this C is this phi. Okay, so this phi in shorthand is just this, and that is this that. Therefore, this is CC dagger in shorthand. This is CC, this is C dagger, this is C dagger, C. There is some 2L cross 2L matrix. Now we are almost there. Remember the original C matrix and F matrix that I defined? I defined it somewhere, right? So the original C matrix and the F matrix. So the C matrix was just Cij is this correlation function. And the F matrix was this correlation function. So it defines two L cross L matrices. So this thing can be easily written in terms of two L cross L matrices. So in this step, again, you need to use the anti-commutation of fermions, and that's why you'll generate this identity matrix here. This would be F star, this would be F, this would be C. So this is again a 2L cross 2L matrix. Okay, now the last step is, how do you write Ci dagger Ci in terms of the U's and the K's? So here, all you need to do is express Ci's and Ci daggers in terms of Ck's and Ck daggers, which I already told you. But Ck's and Ck daggers, you can easily calculate their correlation functions from that single spin picture in the tau fermions, okay? Because after all, the state of the tau spin is just described by U and V, Uk and Vk, right? So you just go from here to the momentum basis. In the momentum basis, it's very easy to calculate those guys, okay? So this is the explicit answer, 2 divided by L k greater than 0, uk. Now uk's are of course a function of t, right? Because the spins are evolving under some dynamics. The pseudo spins rather. Ki minus j. Okay, so that's this. By L, k greater than 0, u star k is a function of t, vk is a function of t, sine k I minus j. Okay, good. Now we can sit back and relax because you have all the machinery. Okay, so the point is, whatever you do, suppose you do a Fluke problem or, okay, maybe you have one more step to fill, then you can relax. Let me just fill that step. Sorry. Then I'll explain everything again. So there's just one more step. That step is, suppose again I drive my problem in a periodic fashion such that the problem has a magnetic field G1 for some capital T by 2, a magnetic field G2 for another capital T by 2, then again G1 for T by 2, then G2 for T by 2, and so on. Of course, I could have taken some other periodic function of time, but it's just that this is very easy to write an expression for. And that's it. I mean, that's the only reason I've chosen this periodic form. You could have taken a cosine or a sine. It'll be just a bit more cumbersome for me to give you the interpretation, but the interpretation would be the same. Okay? So if you have this, then the Fluke unitary for a single pseudospin, is just the following. So this is for a single pseudospin. Remember, a single pseudospin just goes around in its own Bloch sphere. So it's just this. And this also we know. This hk as a function of g. This is just g minus cos k minus of that and sine k and sine k. Right? So if I give you a g, then you know what this hk of g is. Right? So that's this thing, and this is how you generate the unitary matrix, and this is the final unitary matrix. But whatever this unitary matrix is, this can always be written in this form. Because these pseudospins are spin half objects. There's a direction. So that's why I put a hat here. There's a unit vector. This tau is your spin variable, pseudo-spin variable, times capital T, which is the driving time period, times epsilon kf. Right? So I can always write this problem like this, right? By using the various relations among rotation matrices of spin halves, I can always reduce this problem to this, right? So all I need to do is find the direction of the magnetic field for you, right? So you see, in a periodically driven transverse field problem, just like the undriven problem where I said that there were these, so let's see. So suppose you have an undriven problem. In the undriven problem, at each k there is an effective magnetic field, right? Which is different for different k's, right? So for the undriven problem, there are these Bloch spheres in tau space, and at each Bloch sphere, there is a magnetic field direction. This is for the undriven problem, okay? And of course, for the undriven problem, I need to give you a starting wave function. The starting wave function tells me an initial point on the Bloch sphere for all the Bloch spheres. So maybe the initial point here is this. Maybe the initial point here is this. Here it's maybe this. Here it's maybe that. Then there is a natural dynamics and a natural conservation law here, which tells you again that this problem is integrable in the undriven case. There is this and there is this point. So all that can happen is you draw a plane which contains this point and is perpendicular to this line, and all that the point can do is to make a great circle on this plane. You understand, right? This is the only thing it can do on the Bloch sphere, right? So the point only travels like this. You can see my finger, right? In the undriven problem. Similarly here, the point only travels like that. Similarly here, the point only travels like that. This is for all time. And these are your conservation laws. These are your conservation laws for your dynamics, right? So there are these extensive number of conservation laws for the undriven problem. It's clear geometrically what's happening. Of course, you can write algebraic expressions also, but that's it, right? These are conservation laws. The conservation law is that the point only travels on this circle. If there were no conservation law, the point would have covered the entire surface of the sphere, right? If there were no conservation laws in this problem, the point would have just covered the whole surface of the sphere. But there is a conservation law. The conservation law is that at each k, there is a magnetic field which does not change in time for the undriven problem, and therefore the point can only traverse along this great circle, along that great circle, and so on. Of course, this circle is determined by the initial condition. So if you take a different initial condition, then maybe you get this here. And then, of course, the circle here is this. So therefore, the system retains the memory of its initial state at all time for this integrable theory in the undriven case. Okay? I hope this is clear to everybody, right? Very good. Now, what happens in the Fluke case? If you're looking at the problem stroboscopically, all that happens is you get a new direction, nk, which is a complicated function of g1, g2, and capital T, and k, of course. So this nk is some complicated function of k, g1, g2, and t. But whatever it is something unique at that k, right? And then if you're looking at it stroboscopically, it's exactly the same story here. It's exactly the same story here. By the way, this thing is called the generalized Gibbs ensemble. And in the periodic problem, all that happens is you get a dressed magnetic field direction. That's all that happens. If you're looking at the problem stroboscopically, and then I guess I don't need to draw any more, then of course that object, that dressed version of this picture is called the periodic generalized Gibbs ensemble. That's it. So even the periodically driven transverse field Ising model does not heat up to infinite temperature, because there are again these n conservation laws there. Okay? But let's go back to where we started. I wanted to tell you how to compute that entanglement entropy, and I have fulfilled my promise. So you just again look at this motion. So UKs and VKs are nothing but tracking this circle, right? Those are the functions of time. So you compute those functions of time, you plug them in, so you know these matrices as a function of time. Because you know these matrices as a function of time, you write this matrix. This matrix gives you 2L eigenvalues, and these also change as a function of time in a non-trivial way. But now the computation is very straightforward. You get those eigenvalues, and from that you compute the density matrix using this formula. The entanglement entropy of the reduced density, right? And that's exactly what I had drawn in those graphs. So these are the steps of the calculation, right? So hopefully I have convinced you of two things. A, in the undriven problem, there are these extensive number of conservation laws. they have a very nice and a simple generalization to the driven problem if you just look at stroboscopic intervals of time for the transverse field Ising model. Okay? And the second thing I've shown you is how do you just solve that dynamics and compute for the entanglement entropy of the driven problem. That's exactly how I generated those graphs. Okay? So, yeah. So it's let me take a short pause and take your questions before I start the next topic, where I won't show you so many equations. Yeah. Is there any questions? Of course, you can ask me later also. But if there are any pressing questions, you can ask. But just go back and think a bit about this and it'll become clear. But it's a reasonably interesting thing to do, right? This entanglement entropy is extremely hard to calculate for any generic quantum theory. So here it's a very nice example of where you can just literally calculate it and see many things in a simpler integrable model, right? But there are some very interesting structures even here. So
basically, if you have a problem which you can reduce to a problem of sort of non-interacting fermions, then in general you can write down the entanglement entropy in terms of these 2-point coordinates,
yeah.
and so.
Exactly. Right. It's still a bit of a task to see what the final matrix is, whose eigenvalues this entanglement entropy is. There are various ways of motivating it. I chose to motivate it like this because I personally think it's the simplest. But, yeah. Okay, good. So let me erase the board and now tell you something else where I won't do so much algebra. Okay, but as I said, you can go through these steps and maybe it'll become clearer to you. Okay, so now I'll introduce something which will make it very striking. I'll again stick to a non-interacting problem. Only in my last 2 lectures tomorrow will I talk of interactions. I'll still stick to a non-interacting problem of fermions, but I'll show you that in a Fluke system something very interesting can happen. So what is that? Suppose you take a 2D non-interacting fermion system and you localize it. So what that means is you just put a disordered potential in it, right? So the one body states localized, right? Then, if all the states in the bulk are localized, then we know that in an Anderson insulator, there are no surface edge states as well. Everything is localized, okay, in an Anderson insulator. You can show that. But in a Fluke system, that is not true. If you solve for the spectrum of a Fluke system, there can be situations where even though the bulk of all the, so you find the eigenmodes of the Fluke theory, right, Fluke unitary, and you literally just see how they are located in real space. So you can have situations where in the bulk, all the modes are localized, but in the boundaries you have chiral modes. It can happen in a Fluke system, and this can never happen in equilibrium, and therefore when people first found it, they called it anomalous Fluke Anderson insulator. That was the name given to it, okay? And I'll show you pictorially how it can happen and why it happens, and yeah. Here I'll show you a very fine-tuned point where you can just solve everything by pure thought. And again, if you move away from that fine-tuned point, you have to then do numerics, which some people have already done. I'll give you those papers. And but you still would know that the chiral mode has to be stable from some general arguments. Okay? So why can such a distinction even arise? So let's just draw some pictures and it'll become evident. Okay, so that's the aim now. So essentially what I'm trying to say is that in Fluke problems, there can be interesting topological structures. In non-interacting Fluke problems, there can be interesting topological structures which are absent in equilibrium. That's exactly what I'm trying to say. So let's think of the simplest problem. Let's say take a chain. So maybe there's some dimerization in this chain, and there's some whatever fermions hopping. So I'll be very schematic now, okay, because most of it is well known. And anyway, I have inflicted enough algebra upon you for a day. So this kind of a problem would, of course, have a two-band picture. So there's no driving here. Okay, so the Brillouin zone goes from minus pi by a to plus pi by a, where a is some unit cell, right? And this guy is energy. So of course, maybe this problem would look like this. Of course, you can solve this problem, but I'm not solving this problem. And so if you half fill this problem, you'll get a band insulator, right? Everybody's with me, right? So let me ask you a question now. Suppose there's some very complicated problem and I still need to diagonalize it on a computer, I don't know what. But can I ever get something like this? So let me just draw a diagram for you. Can I ever get something like this? It's a very basic question. Is this thing possible? Or does it violate something? Periodic what? This is correct, but what is this? What boundary condition? That's correct, that's correct. So the answer is completely correct. Pi by a has to be identified with minus pi by a. So there's a periodicity, right? Because that's what happens in a periodic potential problem. So because pi by a has to be identified by minus pi by a, whatever this value is, it has to be the same value here. So this cannot happen on general grounds. Good? So this already teaches you something. This teaches you that in this problem, in this 1D problem, if you think of K effectively lives on a circle, okay? But E lives on the real line. So the topology here is that of a cylinder. Now let's think of the Fluke problem. In the Fluke problem, if you remember, I already told you that the Fluke eigenvalues are also periodic. So for example, you can define them in this interval. Remember that? So what does that tell you? That tells you that if you go from an undriven to a driven non-interacting problem, the topology changes. So if you wish, this is K. And if you wish, this is EF. Everybody understands that? So there's a fundamental change of topology. This goes to this. So certain structures here can never be deformed to this. And those structures which can never be deformed to this appear anomalous in this language. Do you understand, right? I mean, there are certain structures here which can never be deformed to this, so they obviously have no equilibrium counterparts. That's why people call them anomalous, but there's nothing anomalous about them because they're very natural here. It's just that they cannot happen here, but that's simply because the topology here is different than the topology here. That's it, okay? So, of course, when people find it the first time, it's very surprising but actually this is the real reason. Of course, people who found these things the first time, and I'll give you a couple of very nice references, they perfectly well realized this, and those original papers were very beautifully written. So this is already an important distinction. So what do I mean by certain things cannot be deformed to this? So suppose you draw this band here. Suppose you draw this band here. This sort of looks like this. So sorry for my drawing, but it sort of looks like this, right? This band. Okay? This band sort of looks like this. But suppose I draw something here. You'll see that you have no counterpart of this here. So suppose I draw something here. Again, a band here. Now this is a bit hard for me to draw, but I'll try to draw it nicely. So now I have to fulfill two conditions. I have to fulfill the fact that minus pi by t is also identified by pi by t. Earlier, there was no such restriction because this is an open direction. There's minus infinity to plus infinity, right? So you see, here I can draw a loop which has a winding, a non-zero winding, right? So this kind of a thing has, for example, winding of 1. Okay, so this has a non-zero winding, but there's no analog of that here because to create this winding, I needed to use the periodicity in both the directions. Okay, so this has no analog here. So certain Fluke bands have no analog in equilibrium. Okay, so more precisely, any Fluke band which has a non-zero winding has no equilibrium analog. Okay, so it might be more instructive to just cut open this thing. So I'll just do that and draw diagrams like this. So it will appear more intuitive for you. But I just drew it here like this so that you realize that this is a winding. So let me just cut open this torus. Let me draw 3 diagrams. I'll draw 3 different diagrams. So this is like momentum again, and this is like quasi-energy. So just like this point is identified with this point now, this point is also identified with this point now. That's the only difference. So I'll draw 3 diagrams for you. Okay, so let's draw a Fluke band like that. Something, okay, so let me be careful. So maybe something like this. This Fluke band has 0 winding. So this has W equal to 0. Let me draw another Fluke band for you. This is essentially what I drew there. So this is fundamentally using the periodicity of this direction. This has a winding 1. Similarly, if I drew something like that, this has a winding -1. Okay? Because here I'm using this periodicity in a very essential way, right? So it'll become clear, more clear even in this picture. So suppose I draw something like this. Then I need to switch here because there are periodic boundary conditions in both directions. And then maybe I do something like that. This Fluke band has W equal to +2. So these kinds of Fluke bands have analogs in equilibrium also. You can easily see that. But there is no analog of these kinds of Fluke bands in equilibrium, right? Okay, is this point clear? That's because these things fundamentally care about the periodicity of the EF variable, right? But this thing for this is not so important, okay? See, I mean, you can see this very clearly here. I drew something here, then I came here. Why? I had to use the periodicity. Then I drew something here, right? So this dotted line is just a guide to the eye. It does not mean anything, okay? It's just a guide to the eye. So I'm just cutting this thing into this thing and drawing these pictures for you. So now comes an interesting point. If you fully fill, so let me call these bands which have non-zero binding, let me call these bands which have non-zero binding as chiral bands. So if you fully fill a chiral band, or a chiral mode, you can show that it carries a quantized current. So let's see that. So let's just concentrate on W equal to +1. Let's just concentrate on that picture. So to find current, basically all that you need to do is calculate the group velocity, or basically the average group velocity in a band, and just multiply it by the density of fermions in that band. That's the meaning of a current. Okay, so let's see. So average group velocity. So average group velocity is again given by the derivative of that function with respect to k. This is how group velocities are defined, right? And I need to sort of take an average over the entire band. Now comes the interesting thing which makes this calculation very simple. You see, no matter what you do, you could have changed this band slightly or whatever, no matter what you do, this point and this point are identified, right? So this point and this point are identified, this point and this point are identified. So calculating this average is just calculating a slope of a straight line, because this point and this point are identified, and so you cannot change those, and you have those restrictions, right? So the change here is 2 pi by t, and the change here is 2 pi by a. That's it. That's the average answer. This cannot change. This is just set by boundary conditions, if you wish. So this whole answer is a by t. A is some unit cell length again. So that's the average group velocity. It's simple to calculate because whatever I know that if I do the average of this, I can deform this situation to this situation. Similarly, the average current is the density of charges here times this average group velocity. But now again, suppose I'm thinking of an insulator, like the band insulator I drew upstairs. There's basically 1 electron per unit cell, right? So if I just think of that, then the density is again naturally 1 by A, and that's multiplied with Vg. So this is 1 by A times A by T. So this A and A cancels, and this becomes 1 by T. So it's quantized. So basically it means that there is transport of one particle per driving period. Transport of one particle per driving period in this problem. Okay? In fact, more generally, this is W by T, where W I have defined above. Okay? So if the band has no winding in that picture above, then basically you don't generate a net flow of current. Okay? Whereas if it has a winding, then you do. But now you should ask me, oh, I was talking of insulators. What does it even mean to transport something? So let me just give you a feeling for that. Let me give you a feeling for that. So here is a situation where the micromotion is really important. You see, in the Fluke physics, of course, the unitary matrix has a lot of information, but if we want an analogy to some sort of an equilibrium problem, we generally just focus on the stroboscopic times, and then there is some analogy to equilibrium undriven problems, and then we just look at things at stroboscopic times. But sometimes you can miss some information if you're just looking at a problem stroboscopically. I mean, just to give you an illustration, suppose there is a fan blade which is moving like this, and you're just looking at it stroboscopically. Then, whether it's moving or it's stationary, you may not be able to figure it out. You understand, right? Because stroboscopically is like one time period. So there's your fan blade. It may be doing this, but after one stroboscopic time, it has come back to where it was. Then after another stroboscopic time, it has again come back to where it was. So if you just look at stroboscopic times, how do you distinguish between whether the blade of the fan was doing this or it was just stationary? right? So in certain cases, micromotion is very important. So for example, to even interpret something like this, it's very important. So what do I mean? So let me just give you the rough picture. So again, it's an insulator. So there are some points on which the sort of the fermions are localized, right? So you make one full cycle, stroboscopic cycle. If the fermions are just doing this, they are just jiggling back and forth, then there is no net transport across this fictitious dotted line, right? However, imagine a situation like this, where in one full time cycle, this fermion has gone here, this fermion has gone here, this fermion has gone here. In fact, if you just look at it stroboscopically, you cannot distinguish between this picture and that picture, right? There's nothing to distinguish between this and that if you look stroboscopically. But there's a net transport of 1 unit of charge in one time period here, in this problem below. But there's 0 transport in this problem above. Okay? So that's the distinction here. Okay? So it's a topological distinction. Good. So then I'm not doing very well with time, but maybe let me just take maybe 5 minutes extra, and then because I just want to finish this thing, and I'll just draw some pictures and I'll give you the original references. In the next 2 lectures, I'll want to start with the interacting theories. Okay. So now, as I said before, these chiral modes, because of these winding, they are a speciality of the Fluke driving. So let me give you a problem where I'll show you that if you just look at the bulk states of these fermions under a unitary evolution, you will realize nothing about the problem, but there are actually chiral modes living on the edges. Okay, so let me just give this very artificial problem to you. But the advantage of this artificial problem is that if you add small perturbations to this artificial problem, the story remains the same. But this artificial problem, I can just solve on the board without doing basically any calculations. So I hope you are with me and you see roughly why there are these important differences for non-interacting problems. So let me define this extreme or slightly idealized problem to show some of these chiral modes. So this was first done by Titum, Berg. This is a very nice paper. Rudna, Raphael, and Lindner, PRX 602103, 2016. You can look at the details here, okay, but let me define the problem for you. So I'll define a particular Fluke problem and you'll see what's happening. 1, 2, 3, 4. I have to just draw 4 pictures carefully. So let's call that 1. Let's call that 2. Again, it's like a piecewise driving, just like this, but I'll define the pieces for you. So it's going to be a completely non-interacting story of fermions, but I'll just define it, and you'll see why it's very interesting. So that's 3. So this is the cycle. So what is the cycle? So the Hamiltonian here is simply nearest neighbor fermionic hopping. That's it. That's the Hamiltonian with some well-chosen coupling. I'll come to this well-chosen coupling. Okay, but these hoppings are turned on only for a subset of bonds during time capital T by 4, only for another subset of bonds during the rest of the time capital T by 4, a third subset of bonds during the next T by 4, and the fourth subset of points during the remaining T by 4. And it keeps repeating. Of course, if you add up the subsets, it covers all the bonds, but the subsets are different. So what are the subsets? So let's use some, let's use some different colors. So here, these are the subsets. So what I'm saying is that this hopping is only turned on for these bonds here. Only turned on for these bonds here. So if there is a spin here, if there's a fermion here, it can only hop here. It cannot hop here or here or here. There's no channel for it to do it. Okay, it can only hop here. Okay. Similarly, I hope this green, should be visible. It only does that here. Then again I'm back to horizontal where I color the remaining bonds. Okay, and then I'm back to vertical where I again color the remaining bonds. Yeah, those were the things I excluded, yes. So as I said, this stays for T by 4, 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 and this keeps repeating itself. Now, so the setup is clear, I hope. It's a very, very simple setup, extremely simple setup. Now I'll choose a particular value of this j. I'll choose the value jt by 4. So remember the natural period here is t by 4 for one of these sub-cycles, and j is this coupling. I'll choose this combination jt by 4 to be pi by 2. Now why do I choose that? This I leave as an exercise for you because I don't have time for showing this. I want to finish not too much over time. So if I choose jt by 4 to be pi by 2, then within this time t by 4, if there is a fermion here, with unit probability it will move here. Unit probability, not with probability half or 1/4 or anything, with unit probability it will move here. Okay? So if there is a fermion here, it will definitely move here if I choose this coupling. It's actually very easy to derive. I encourage you to derive it if you don't already know it. Okay? So now let's look at 3 points and let's imagine that there are fermions there. So let's look at this point A. Let's look at this point, this point B, and let's look at this point C. Oops, sorry. Let's look at this point C. Let's first focus on A. Suppose there's a fermion on A. So then during this first T by 4, with unit probability, it'll move from here to here. Right? All of you agree? Well, you have to show that this happens with unit probability, but you can show that. Then this guy moves here. But there is a wavy line here. So again, with unit probability, it'll go here. Then this guy moves here. With unit probability, it'll again go here. Then this guy moves up. So with unit probability, it'll just come back to its starting position. So if you look in the bulk modes, and if you just follow the Fluke unitary for one time period, you will see no change because any fermion, wherever you started, it'll just come back to itself. So for bulk states, U of t is identity in this problem. I don't even have to do any calculations. For bulk states, it is identity, because no matter where you start the fermion, it'll just come back. After all, it's a non-interacting problem, right? So I just need to find one body states, and then I can just fill them up, right? So, okay, good. But so, now suppose the fermion starts at B. Then something interesting happens. So let's start the fermion at B. So the fermion is here at B. Then in one T/4 cycle, it moves here to this point. So it moves here. But now you see, it has nowhere to go, because this hopping is off, this hopping is off, and this hopping is off. That's a boundary effect, right? Then in the next cycle, it hops there. So it moves forward again, right? But then it comes here. And then in this cycle, it again has nowhere to go, right? So it hops in this direction by 2 steps. Okay, this, oh, sorry, I'm making a mess, but okay. Similarly, you can show that this fermion, if you put it here, by the same argument, you can show that this C fermion moves like this and then like this. Okay, good. So then, if you just extend your imagination a bit, then what is going to happen is, that the states look a bit like the following. I'll just draw a picture. States look the following. So if you take like a big system with open boundary conditions, inside there are these circulating currents. But you would have never known that these are circulating currents if you just looked at the unitary evolution for one full cycle. In the bulk, there are these circulating currents. On the boundary, there are these chiral modes. Okay, there are these chiral modes. In fact, if you solve for the spectrum of this artificial problem that I told you about, it's very easy to solve. So in fact, let me just use some k parallel, because I just want to go along chiral modes. It's actually technically a 2D Brillouin zone, but for drawing, it's enough. So the bulk modes have a 0 Fluke energy, right? Because U of t is identity. But the boundary modes are chiral, so they have to have some winding from our earlier argument, right? So there is a +1 winding. That +1 winding corresponds to a positive velocity, so it's this mode. And there is a -1 winding. Sorry, my drawing is very bad. These 3 things should cross at the same point, but okay, anyway. So this is like plus velocity, and this is like minus velocity, right? So there are these 2 chiral modes. This is what happens if you just take this toy problem. Now I'll be very quick and I'll stop because I'm really over time. Sorry for that. Now, imagine that you take this problem out of this artificial limit. Maybe you put some disordering chemical potential, and maybe you put even some small hoppings on these rest of the things. See, here the hoppings were exactly 0, but maybe you put some tiny hoppings in the rest of the things, right, in some way. As long as your disorder strength is much, much smaller, and these hoppings are much, much smaller than this unit, pi by t, because this winding is basically related to this periodicity in pi by t. So as long as whatever fluctuations you are giving is much smaller than that periodicity, it can never destroy it. As long as you do that, then in that deformed problem, you cannot solve it so easily, just from pure thought. You have to sit, write a computer program and solve it. But in that paper, you can see diagrams for that. When you solve for that, the spectrum deforms from this, and it looks like this. These flat bands just deform to something else. And these chiral bands are also not straight lines, and they deform to something else. But okay, they also keep on, they exist at all quasi-energies. They are also existing at these energies. And something like this happens. Something like this happens. Okay? So the chiral modes continue to exist at all quasi-energies, and the bulk modes are still localized, because it's not hard for you to imagine that even if you disorder this problem, these modes will stay localized. It's not hard to imagine that, right? But of course, the proof and all is given in that paper, and you should read that paper. And so in this phase, all the bulk modes of the Fluke problem are localized, but if you look at the boundaries, there are interesting chiral modes, and this could have never happened in equilibrium. So I'm really sorry for taking so much time, and maybe I'll just stop here. Thank you. Yeah.